Yes. Yeah. So you guys can see the screen. Okay, good. So this is problems. So challenges and thrills, we did a few problems, and I expect you guys tried. If you cannot get something, you should ask me. Okay, if you cannot find it, you should ask me. Okay, so problems from Niven. 1 minute. Niven and Zuckerman. I don't know if it's man or man. I don't know. Whatever. I mean, yeah. So 1.2 problem number 11. And so this is, I think, simple. So show that 4 does not divide n square plus 2 for any n. Okay. So how do we do this? That's right. Yeah, n square is either 4k or 4k plus 1. Yeah, and said in the language of congruences or residues or quadratic residues, you can say that n square leaves a remainder of 0 or 1, right? Other things are not possible, right? So, well, what does this mean? That if you take n square plus 2, it will either be 4k plus 2 or it can be 4k plus 3 also. But it cannot be a multiple of 4. Right? Fairly straightforward. There's really nothing to it. Is it clear to everyone? It's not clear to anyone, just tell me. Okay. So then we'll move to problem 12. So you have to tell me because I will not know. So problem number 12. So A and 4 leave GCD 2. B and 4 also leave GCD 2. So 2, just a second. A and 4 and B and 4, the GCD is 2. Okay. So we want to, this is given to us. We want to show that A plus B, this is GCD 4 divides A plus B. Right? So again, how do we do this? Okay, A has to M, B has to N. Why are M and N co-prime to 2? Perfect. That's perfect. Yeah. So basically M and N are odd. Perfect. That's right. Good. Right. And so this is at least 4, right? I mean, it's at least a multiple of 4, maybe higher powers of 2 is also possible. We cannot say, but at least for good. So these are easy questions, but one should do them to get comfortable with these notions. Okay. All right, good. Let's move on. Okay. Again, interrupt me if you don't understand something. So it's just straightforward questions. Okay, 13, 14, 15, 16. The 13 prove that n square minus n is divisible by 2, but that is something which we have shown. So let's just try the last one. Okay, this one, we have done this, right? N to the power 5 minus n is divisible by 30. I think we had done this at some point. Yeah, so let's skip that. So now if n is odd, prove that 8 divides n square minus. This is a very nice one. It's easy or not, that's a different thing, but this is a very nice problem. Yeah, just before solving this, just think about this. Look at this, right? See, n square minus 1. Okay, n is odd is given. Yeah. N is odd. So we know that n square minus 1 is even. But you see, something special is happening here, right? N square minus 1 is divisible by 8. Okay. And nothing is given about n, just that it's odd, the most basic condition that needs to be there, right? That's the wonderful thing. Just think about it, right? It's something good. So these kind of good surprises keep coming in number theory. Okay, let's try to prove this. It's easy to prove it. That's not the point. So let's try it. Sorry, say that again. 8 will always leave remainder 1 or 4, or when divided by any n square. Uh, yes, yeah, certainly, right? 0 is obviously possible. When divided by any n square, so 0 is also possible. Okay, so then 8 will leave remainder 1. I mean, I don't understand that. No, I mean, is it something opposite to what you want to say? I mean, because if you divide 8 by, I don't know, 50 something, then n square. Yes, that's what I was thinking. That's right. Yeah. So you are considering residues of squares modulo 8, right? Yeah, that's what. So you're saying that this leaves a remainder 1, 4, or 0 modulo 8. And this you're saying is something that can be easily checked. Right. And then there's nothing more to the problem because 4 and 0 are not possible. It has to be 1. Yeah. So yes, this is what happens when you do congruences. The problems become very simple, right? But can we do it without? So this is because you can just check. I mean, n equal to 1, then you check it square and check. N equal to 2. I mean, if n is equal to 2 mod 8, n equal to 3 mod 8, and then you square them and see what you get. That's all right. So then it becomes very simple. But can we just say it without congruences? Is it possible? That's right. No, n has to be odd. That's true. Otherwise, the number is odd, so it cannot be divisible by 8. But when n is odd, yeah. So the question is, I mean, if n is odd, then you have to show this, right? So n is odd, yeah. Then you want to show that it divides this, right? Yeah. You want to show that this happens, right? That's the thing. And yes, so by congruence is easy. Does anybody have an alternative way? Any alternative way? Yeah. Yes, right. I mean, if you write it as 2k plus 1 and then compute the square and so on, you will get. That's right. That's correct. It will get it. But just a small, what I wanted to emphasize here is just that, I mean, one can just factorize. Yes, exactly. The factorization. So you should just try to factorize it. And then, so then what can we say? N is odd. Yes, these two are not consecutive, but yeah, they're consecutive even numbers. No, you're right. You're consecutive even numbers. Yes, and that's right. So if you have two consecutive even numbers, one of them will be a multiple of 4, right? And that is, I suppose, clear, right? So two consecutive numbers, see, obviously we understand it by this common sense, but two consecutive, but we should also just know the proof. Two consecutive numbers, then one of them is divisible by 4, right? So, I mean, this is because, I mean, if one of them is not divisible by 4, then the other one is 4k plus 4. So the other one has to be, one of them is not. So it is just easy, yeah? But it's a very fantastic result. If it's the beginning of many results like this that will come. So yeah, okay, so this is easy. So we're just doing easy stuff. I mean, we should just do these things fast, so that we, so what's the next question? Prove that if x and y is odd. Okay, so this is again similar, so I will not, let's not do it. So 16, yeah, prove that if a and b are positive integers, satisfying this, yeah, that the LCM is the same as the GCD. Prove that a is equal to b. So if the LCM, so this is the GCD, sorry, if the GCD is the same as LCM, then show that a equals to b. Yeah. So I mean, just do it. I mean, I know some of you have done it. I'll just come in a minute. I'll just take some water and come. Okay. Yes. Yes. So yeah, someone knows it. This is easy. Yeah, so we all know that the GCD and the LCM is never, is usually never same, right? Sorry, what's the last thing? Smaller multiple? It will be smaller. Yeah, it will not be more than the minimum, right? Of the two. Yes. Right. So that's right. I mean, this is less than or equal to the minimum of A and B. Is that okay? Is that clear? Yeah, because it's a common factor, right? So you cannot get more factors than the smaller of the two numbers, right? So this is fine. And then, but then we know that for the LCM, I mean, it is like this, right? But then because these two are given to be equal, so these two become equal. But then if minimum of two numbers is same as maximum of two numbers, then it means that the numbers are same. There is no other choice. Easy question. Yeah, any doubts? It's fine. Right. It's a very, but it's an interesting question, because what this is saying is that if you take the set of natural numbers, yeah, and you take the set of pairs of natural numbers, this is n cross n, it means pairs, right? Pairs of numbers. Yeah. So you would have seen the Cartesian product of two sets and so on. But either ways, I mean, this just stands for pairs of numbers. This is just a set that just stands for pairs of natural numbers, ordered pairs. So like 1, 2, 2, 1, they will be different and so on. It will have all pairs, all possible pairs. Okay. What this is saying is, what this problem is saying, one way to see it is you take any number and you send it to a pair of numbers. What pair of numbers will you send it to? You, oh, hold on. What am I saying? No. Sorry. No, that doesn't make any sense. So if I take a number, can I do the GCD? And just 1 minute. If I send it to, just 1 second. No, this does not work. Let's try. If I take pairs of numbers, okay, so here this pair doesn't mean GCD, just taking pairs of numbers. And if I send it to, let's say, GCD of the two numbers, comma, the LCM of the two numbers. Okay, so both the sets are pairs of natural numbers. I take a pair of natural numbers and I send it like this, yeah, to the GCD and LCM. Okay, then is it possible that two different pairs? So what do I mean by two different pairs? I mean that this is different than this means that either A is not equal to C or B is not equal to D, right? So then these two being equal means what? Both the components have to be same. You can look at it as points on the plane, right? A comma B, C comma D. So two numbers, I'm sending it to GCD comma LCM. And again, these two numbers, I'm sending it to again GCD. That's the rule. Okay. I'll do that with all the pairs. So then my question is it possible that two different pairs give you the same GCD and LCM? So there are two numbers, they give you some GCD and LCM. If I take some other two numbers, is it possible that the GCD and the LCM is the same? Yes, anyone? If the question is not clear, you should tell me. So for example, you can take like 2 comma 3, then this will go to 1 comma 6, right? And if you take 4 comma 6, then this will go to 2 comma 12, right? So is it possible that two different numbers go to the same number? No. Why? Why? No. The question is not that the GCD. No. I'm saying yes. So that's okay. So what I'm saying is that the GCD of this is same as GCD of the other pair, right? There are two pairs of numbers, right? GCD of the first pair is same as GCD of the second pair, right? And the GCD and the LCM of the first pair is same as LCM of the second pair. Can that happen? Yeah. So can you give example? 2 and 12, exactly. That's right. So this is not an injective function. Okay. It's a very natural function, but it is not an injective function. Two things collapse and they become the same. Okay. It would be very interesting if one can find some, injective functions. Injective meaning that, two different pairs go to two different pairs. Yeah. So what that kind of function would do is it would tell you some sort of it would tell you something about the structure of n cross n, right? I mean, n cross n is points. Yeah, it's grid points, right, in the plane. 1 comma 2, 2 comma 3, 5 comma 10, and so on. These grid points, but it is more than just grid points, right? There is an addition, there is a sub multiplication, and so on. And then there are the natural things like GCD and so on, right? So it would be very interesting, right? If one can sort of what that would be mean is sort of you're rearranging the things, right? Rearranging the points in the plane, sending one point to another, and still everything just fits. This is not that kind of function. Yeah. So basically it is saying that knowing the GCD and the LCM is not enough to recover the number. Is that point? Yeah, clear? Yeah. Knowing the GCD of two numbers and LCM of two numbers is not enough. In fact, we have done problems, right, where GCD was given, LCM was given, and we asked to find number of numbers. Okay, we didn't discuss that paper. I don't know if we discussed or not. I don't remember. I think we did not, right? So, and we had discussed this in class also, how many numbers. So there are many numbers. It's possible, yeah. So this is not that kind of function. So maybe as a homework, someone can try to think, some sort of a rearrangement of n cross n to n cross n, which is a, okay, not like you can say, okay, I'll take 1 comma 2, I'll send it to 2 comma 1. I'll just switch the coordinates. That is fine. But that is not number theoretic. That is a geometric thing, right? Where you are just switching the coordinates. So that would mean that you are just taking this line and you're reflecting the plane about that line, right? So you can understand, right? Like 1, 0, or this 0, 1 goes to 1, 0, and so on. So that would be a geometric thing, geometric way to consider, permutation of this infinite set. But is there a number theoretic way? That seems to be, answer seems to be no. Answer seems to be no, but there is no, I don't think, theorem like that, because the statement itself is not clear. But try to see if you guys can think of something. It's an interesting question. I initially felt this question is a little like that, but then this is not like that. It's different. A, B, C, and D will have a common. Okay. Yes, right, because the GCD is the same. So the GCD, which is same, will be the common divisor. That's right. You're right. Yeah, that's a good point. Yeah. So that basically says is that, yeah, many numbers can go to the same number, but it's not an arbitrary set of numbers that go to the same number. There is a certain description which numbers can go to the same number. Yeah. These are the functions like this. If one can find good functions, these are the ways to solve problems, harder problems. Okay. Like Chinese remainder theorem was like that, right? Recovering a modulo 12 understanding from modulo 4 and modulo 3 understanding. Yeah. So yeah, let's keep going. Yeah, and just a little, please try this question. This is an interesting question from the previous question. I think one can think about. First, if you have given that n is odd, can you tell if n to the power 4 is divisible by 16? Is it true? Or let me just try to change this. N to the power 8 minus 1, because I think that is a little bit of an anomaly. Is n to the 8 minus 1 divisible by 16? Is it true? So question mark. So we saw that n square minus 1 was divisible by 4. Is it true that n to the 8 minus 1 is divisible by 16? So we can try to see. So first we can try to factorize it a little bit. Right? So then we have n minus 1, n plus 1, n square plus 1. Yeah. Is this divisible by 16? Can anybody tell? No, both will be even. Yes, one of them will be even. Both will be even, right? Because n is odd. Yeah, certainly both are even, but yeah, so can we use that? Yes, it's divisible by 8, right? That this part is already divisible by 8. Because I mean, you understand one of them is a multiple of 4. And then this is also even, so this gives a factor of 2. And this is also even, so it gives a factor of 2. So I will, in fact, we get 32. Right? So it is true. Yes, the answer is correct. Yeah. So what is happening? I'm trying to increase the power of 2 here, and the power of 2 here is also increasing. Right. That's what seems to be happening, right? When you have n minus 1 is divisible by 2. When you do n square minus 1, well, it's divisible by 8, in fact, but I don't know if that is a coincidence. 4 is not a coincidence. But anyways, that's it. And then, so let's just check into the 4 minus 1, right? What happens to into the 4 minus 1? So I mean, we are sure that you'll get something more, right? Yeah, this itself is divisible by 16. Right, and so this is divisible by 38. So then, is there any pattern? N is odd is the underlying thing. Yes, powers of 2, but which power? Uh, yeah, so it seems like it is like 2 more, right? Power is 2. So what seems to be true, we don't know if this is true, is if you do this, then this seems to be divisible by 2k plus 2. 2 to the power 2k plus 2. Right? Four. No, yes, I mean, it is true for 8. So it's obviously true for 4. Yeah, is that this you're saying, right? I mean, yes, it's divisible by 8. So it's obviously divisible by 4. Yes, so 2 more. I mean, it seems like 2 extra powers are coming. That seems to be the pattern. I mean, even if you forget about the 2, even if you can prove that n to the power 2k minus 1 is divisible by 2 to the power k, that itself is a nice thing, right? Very nice thing. But that it seems like that cannot be done so easily just by checking congruences. Right? I mean, you cannot, because you won't know, right? N to the power 2k mod 2 to the mod 2k mod 2 to the power k, what remainders it would leave you, how would you know? Right? So that's an interesting and challenging question. So please try to think about this. I mean, you can just try to show this. I mean, it would be good enough to just show this. Right? Seems to be correct. And I think it is correct. There is a certain thing called the exponent GCD lemma, or lifting the exponent lemma or something. It's a very powerful tool in more advanced number theory problems. But just from this pattern, I thought we can discuss this. Think about it. We can try to take it next time. All right. Note it down. Let's move on. So what's the next question? Did I ask 17? No. So then I asked to do 21. So these were the easiest problems, I think. So we did 21. Prove that if an integer is of the form 6k plus 5, then it is necessarily of the form 3k minus 1, but not conversely. All right, so this is problem number 21. Yeah. So if n is a number which is of the form 6k plus 5, yeah, then the question is show that it is of the form 3k minus 1, but not conversely. Yes, that's right. So 6k plus 5. So just trying to make it in that form, right? So it's one less than a multiple of 2, right? So numbers of the form 6k plus 5 come from numbers of the form 3k minus 1, right? So then why is the converse not true? So if you take a number of the form 3k minus 1, start with 3k minus 1. Now what could it be? 6 in terms of 6k. Well, it's just easy to check. You can, yeah, so how should it be? Sorry. So, okay, so you are saying in the when it is yes, I think that is right. Yeah, that's right. So you're saying that when it is of the form 2k, then it is not true. The converse is not true, right? Because yes, so basically from here there are, and what you have said is correct, and it is more or less what is being asked. But you have to tell when is the converse not true. If you tell when is the converse is true, then as an answer that is not, that's not complete. I mean, I understand what you're trying to say. Oh, is that? So I think upon that, and did you say the opposite thing? Anyways, we'll check it, right? So if k is odd, which means, I mean, if k is of the form, again, I'm just writing k there again, but it doesn't matter. We are, okay, let's not write it because now for now it's just confusing. If k is odd, then the converse is not true because it becomes 6k plus 2. So is that right? Yeah. And if, because I mean, those are the two possibilities, right? For k, when the k is even, then it is true. So upon, I think you said the opposite thing. If I remember, yeah, I think you said the opposite thing. Yeah. I mean, this is, so when k is even, yeah, then it is of that form. Otherwise, but that is not, that's less important than saying that when k is odd, then the converse is not true. Because 6k plus 2 is not of the form. 6k plus 2 and 6k plus 5 are different. You see, this is a general thing that happens, right? You initially start with the natural numbers, and then you make, let's say, two classes, right? Odd and even, right? So either odd or either even. But the odd numbers, let's say when you ask for a finer partition of the natural numbers, when you go modulo 4, then the odd numbers split up into two, right? Those which leave remainder 1, those which leave remainder 2, 3. So what does it mean? That when you take those numbers which leave remainder 1, they are certainly odd, but the converse is not true. Numbers which are odd could also leave remainder 3. So as you keep splitting the number system, or as you keep taking larger and larger modulo, or you could say that, or just, yeah, larger and larger numbers, more and more devices, you get finer and finer information. Okay, so this is like that. I mean, when you take modulo 3, then you have three kinds of numbers: 3k, 3k plus 1, 3k plus 2. But when you go to 6, right, then what happens? Yeah, then each of them splits into two parts further, right? Each of the three classes split into two parts. Yeah, like those which are of the form 3k, they become either 6k, yeah, if k was even, or they become 6k plus 3, and similarly the others. So that is the nature of the thing. So you take larger and larger powers of the prime, or larger and larger divides, then you get better and better information. But it becomes harder and harder to gain that information, right? Computationally and so on. So that's why we start with simple stuff. Like we check if you're given an equation, we check if it's equal, if both are, if one side is even and one side is odd by default or in some way or the other, even algebraically, then we say, okay, there's no solution. But sometimes they may be, that may not be good enough. So up to that partition, they may fall in the same class. So there may not be any contradiction. Then you may go to a higher power. Okay, let's check modulo 4 and you may get a contradiction. Let's check modulo 11. For that, you have to, what residues, quadratics, what remainders they can leave. So you have to sense what I should modulo I should go by. And that can be a very tricky question. And that's the thing about number theory. Yeah? Given an equation, how to know I should check remainder on both sides with what number so that I can succeed in getting a contradiction. I can't just go on checking, with my eyes closed, one prime after the other, or one prime power after the other. So those are the things. But then there are some very interesting theorems in that line, which one can discuss later. So let's think about that later. That some things like, if you check for enough prime powers and it's both sides are equal, then both sides are actually equal, and things like that are there, but one does that at a later stage. But these are some small things that we start with and we see. Okay. So yeah, let's go to the next question. Let's go to question number 24. Prove that no integers x and y exist such that x plus y is 100 and the GCD is 3. Okay, so this is 23. Show that there are no integers x and y such that, oh, I skipped 2 questions. Okay, so I'll do that after this. I did skip, yeah. I'm doing 24 and I wrote, yes, that's all wrong. But let's do this one. After this, I'll do. And also I wrote this condition first. So GCD is 3 and the sum is 100. Okay. So how do we show that there are no such integers? Right. It is just as simple as that. Yes, that's right. If the GCD is 3, then 3 has to divide 100 also, right? And in fact, we also know that the converse is true, right? That if the GCD is 1, then there will be a solution. Or if the GCD is 3 and this side is a multiple of 3, then you can cancel 3 and you can convert it to a situation where GCD is 1. And then there will be solution. That's what we have shown using, I don't know. That's the thing we showed. That was a good thing we showed. And we use it in Chinese remainder theorem and so on. So that's good. Yeah, it's a trivial question. So yes, so I think I didn't think much by giving these questions. So yeah, let's go to 23. Prove that the square of any integer will form this. But yes, again, this one I will not do because this is something that we have done, right? Prove that the square of any integer of the form 5k plus 1 is of the same form. That's again, okay, I skipped this mistakenly, but I'm saying that this is simple because if you take 5k plus 1, you square it, you see it's again of the form 5k plus 1, right? Or you can use congruence language. This section doesn't assume that, but there is. Okay, let me see if there is some question which I actually missed. 21, 22. So then it's fine. It's good, okay? Let's do 25. Yeah, so prove that there are infinitely many pairs of integers x comma y. Let's do this one. Yeah. So 25. So the GCD is 5. Okay. And the sum is 100. Show that there are infinitely many integers. Obviously, natural numbers, there will be only finitely many. Satisfying above. Right? Okay. Any combination. So what do you mean? Yes, exactly. I don't know why they gave this question. Yeah, that's what it is. That's, I mean, you can obviously make infinitely many pairs. Okay. So let's just make it a little more interesting. So if we say that, let's say if we say something like this, yeah, 2x plus 5y equal to, let's just keep it 1. Yeah. Again, in this case, show that there are infinitely many, I have to write infinitely many solutions, integer solutions, obviously. And then today we can also try to find all solutions. That would be so interesting. We know that there is some solution that you can just guess, or also we have proved that fact. But how do you find all solutions? That's the question. Sorry. Yes, yes. Two into, okay, so you're saying, right. Okay. How do you form? Yeah, but any k will not work. You have to, that k has to satisfy x plus 2y, right? And because that y and that y are connected, I mean they are same y. Well, 2 and 5 are, yes, in the sense that 2 and 5 are co-prime means that there is at least one solution. So more precisely, I should say that it has to do with the fact that there is at least one solution. Other solutions are sort of just translates of that solution. Right? Let's try to draw, I mean, it's very easy to solve this either way, but let's try to draw a picture and see. So can we say some points on this? So when x is equal to 0, and y is equal to 1 by 5. Right? So this point is there. And when y is equal to 0, x is equal to half, right? So maybe half is a little bigger, half. And so there is this line, which is what this is. Yeah. And what we are basically trying to say is that this line has infinitely many integer coordinates. Where both the coordinates are integers. Half comma 0 doesn't count. And that's not both coordinates integers. We want both x and y to be integers. So can you tell at least one integer coordinate on this? Yeah, that should not be difficult. So just take y equal to 1. So 1 minus 5 is minus 4, x equal to minus 2. So minus 2 comma 1, right? So you have to take minus 2 very far somewhere comparatively, right? So minus 2 comma 1. Is that right? That's one integer point. Yeah? So now just think geometrically. If you have one integer point, how do you use geometry? How do you find other integer points in a natural way? And we knew that there is one integer solution from a theorem, and we also know how to find it efficiently. We have discussed that, but you can just guess in this case and get it. But then how do you find others? Let's try to move to the right. Yeah. So when this minus 2 becomes minus 1, yeah, which means that x increases by 1, right? The value of x increases by 1, then what happens to the value of y? Yes, that's correct. That's correct. So what happens to, so y decreases, right? By how much does it decrease? 2/5. I mean, one can just work it out from the equation also. Okay. So y decreases by 2/5. So when this becomes plus 1, then y decreases by 2/5. So, I mean, all this can be said very nicely, but we're trying to just see it in a loose way. So, and maybe something that 2/5. Okay. So when y increases by 2, when x increases by 2, then what happens to y? It decreases by 4/5. There is no way it can become an integer so far, right? When x increases by 3, then what happens? 6/5. If I'm wrong, just tell me. Yeah. Right? And similarly, but you would know when is the first time you are going to get something good. This is the first time. You cannot get it before. Right? So x has to increase by 5, and then the y has to decrease by 2. And there seems to be no other way. Yeah, there seems to be no other way, and this is the way, right? So what is all solutions? Minus 2 plus t, minus 2 plus 5, minus 2, I'm just writing it, minus 2 plus 5t, and 1 minus 2t. These are all the solutions. T equal to 1, t equal to 0 is where we started with, right? Then at time t equal to 1, it becomes minus 2 plus 5, and that becomes 1 minus 2. And at time t equal to 2, and we are quite sure that these are all the solutions. I mean, that's what this tells us. right? So that's how a physics student may do the problem. I don't know. It means then that this intuition, if they the kind of which we can use. This is also called parameterized equation of a line, right? You're kind of using a time parameter using which you're capturing the x coordinate and the y coordinate. As I think about it, I've never done it like this. Just try to explain it in this way. So, but yeah, this parameterized thing exists. Right? So you take a parameter t and do it. So usually what we do is yeah, I mean, usually people take, I mean, if we're just going blind, then you take bad parameters. You take the x as t, and then the y becomes something bad, right? But here we have chosen it wisely because and in the way chosen it strategically to get integers and so. And these are all the solutions. Now check that there are no other solutions. That's your homework. It's already clear, I suppose, right? It's already because I mean x has to be an integer, so we have tried all the integers and we check that this is the first time you can get, and this pattern continues. Yeah. So check that there are no other solutions. In general, what happens, that means you can understand if this is 1, a and b are co-prime automatically. So if you find some solution, then you can just take translates of that. That was my point. Yeah. So you will translate this by, and it becomes very obvious if one sees this algebraically. But I just wanted to do it in yeah, these are all the solutions. I mean, this is also very obvious, right? Because if a times x naught plus y naught is 1, then what's the other choice, right? You put x naught plus, you just balance it, right? bt plus, and here you obviously will have to do a, and you have to subtract. And this is the obvious way to generate the other solutions. And these are the only ways because of this physical argument that we kind of did. Yeah. T is, I mean, T is the parameter. T, so T is the value of what, right? So I don't know. T is the parameter. I mean, T is what you can use to easily describe all the solutions. Let's put it like that. First, forget the word parameter, right? T is the value which you can use to describe all the solutions. T is not the solution. Yeah, the solution is not T, right? The solution is this comma this. For example, when you put T equal to 3, you get this, and this is the solution. So T is a parameter. It very easily helps you to describe the solution, and that's what we call a parameter, right? Okay. This kind of thing shows up all over the place in number theory. Okay, there is a very beautiful book. Let me share if I can find it. So this is done. We are ending the class, but I'll just share. Okay, it's 10 to 30. I wanted to share. So this is a very good book which you guys can start trying. If not now, you can try it later. Okay, yes, because of the Zoom and this thing. Yes. I mean, I will discuss some other interesting things in an interesting way, which are also important. I will not discuss everything that is there in the book because I don't know, and also we don't have time. But just wanted to share because I also have good experience with good memory working with this book a little bit. So this is a book which is very interesting. I mean, it's obviously after a few years you will not want to try this. You will see this is tricks, but these are good. So they have a lot of techniques are there to solve Diophantine equations. We just solved the simplest Diophantine equation, ax plus by. We have kind of found all solutions. This book is, first of all, elementary. It's all Olympiad stuff. Okay, elementary stuff, let's just call it. And it has all the different kinds of tricks, factoring, which you can just look at and try. You can just download this book. Don't buy it or anything. I don't suggest that, but it's up to you. You can print it out if you really like it. That's up to you. So there are these methods, and there is a parametric method. Okay, and what we have done is just a tip of the one small tip where parameterizations, we describe all solutions using a parameter, right? Something that helps you to easily describe all solutions. Like this was a T was one parameter. Like you see here, what it does. So these are obviously some tricky questions. So this is the thing, and you basically guess some sort of an identity that okay, I'll take y equal to mx, you know, so on a line, and I'll kind of cut the line with the curve, and somehow I'll guess this solution. In our case, it was simple, but now here it's more complicated. Okay, he starts with these complicated questions. That's very strange. Okay, that's how it is. It's an advanced book. So yeah, I think the classical one it is there. What we did was classical, like linear Diophantine. Yeah, this one, like this ax plus by, then all the solutions are like this. Oh, oh, because sorry. Okay, sorry. Yes, because I should have shared the screen. Sorry. Yes, no. So I just want to say that what we did was an example of the parametric method. And this is a book that you can start working out in the sense that just have a look at it and just see. It's a very interesting book. Okay. So it discusses the different ways in which you can solve Diophantine equations. We just solved one or two, and we'll solve more ones which are relevant, and we'll do it in an interesting way. But there are many methods which obviously I cannot cover, like modular arithmetic method. Bit of it I think did with the Chana, which others were not there, but I recorded it and it's there. But then there's a parametric method. So as I was saying, you guess a parameter and use it to describe all solutions. So this is something which we did today. Okay, but I think we did in by picture and so on. Anyways, let me not say more, just that this is a good book. And so the first chapter, okay, let me say something useful. Yeah, just saying all nonsense will not work. It's this, you can just see, try to find all integer solutions. So you have to just see, he factorizes it and just maybe read a few examples and see. I will cover some of it at some point, small bits, which are, which will help you to do others, okay, if you want to. Yeah. And I will tell you what is important. Yeah, okay. So that is fine, right? So then we'll stop today. Keep trying the other questions. Okay, I will send some other things to also try. And yeah, I hope there's some interesting things we did. Most of it was easy, but some interesting things we did. And yeah, try the questions also which I gave. Okay, that's it. Thank you. Good night. Thank you. Bye. Bye.